Hello, everyone, and thank you for being here. Our project is titled What Drives EV Efficiency and focuses on analyzing Tesla vehicles using MPGE, or miles per gallon equivalent, as our primary measure of efficiency. The goal of this project is not just to describe which vehicles are more efficient, but to understand what actually drives those differences. More importantly, we aim to translate those findings into real-world decision-making. Throughout this presentation, we will move from identifying the problem to building and testing a model, to interpreting the results, and finally to applying those results in a decision-making context. Slide 2, Executive Summary. This slide summarizes how our project aligns with the grading rubric and overall structure. First, we define a clear real-world problem, understanding efficiency trade-offs in electric vehicles. Second, we apply quantitative methods, including descriptive statistics, regression modeling, and sensitivity testing. Third, we communicate our findings through structured visuals and logical progression. Finally, we conclude with insights that are not only statistically supported, but also actionable in a real-world context. Each part of the project is designed to build toward a complete decision model.
This project matters because electric vehicles do not eliminate trade-offs, they simply change them. Instead of balancing gas mileage and horsepower, EV buyers now balance efficiency, vehicle size, battery usage, and utility. These trade-offs are more closely tied to physical constraints like weight and design. As EV adoption continues to grow, consumers are making more complex decisions without always understanding the underlying factors. This project provides a structured, data-driven way to make those trade-offs visible and understandable. Our central research question is, how do weight, cargo capacity, and performance trim affect Tesla MPGE? And what does the Cybertruck reveal about the efficiency cost of utility-focused EV design? We test 4 hypotheses. Heavier vehicles reduce efficiency due to increased energy demand. Higher cargo capacity reduces efficiency due to larger vehicle design. Performance trims reduce MPGE due to higher output demands. And the Cybertruck serves as an extreme benchmark to highlight these effects. These hypotheses allow us to analyze both typical relationships and extreme cases.
Slide 5 highlights that different buyers have different objectives. Some prioritize efficiency and lower cost of ownership. Others prioritize space, functionality, or performance. Because of this, there is no single optimal vehicle, only an optimal choice based on the buyer's priorities. This is why our analysis is framed as a decision model rather than just a statistical summary.
Slide 6. Data sources. Our dataset includes 20 Tesla vehicle configurations collected from official sources. We intentionally limit the dataset to a single manufacturer. This allows us to control for differences in engineering and design philosophy across companies, improving internal consistency. The goal is to isolate how specific vehicle characteristics affect efficiency. Slide 7, Sample Design. This slide expands on the logic of our sample. By focusing only on Tesla vehicles, we reduce variability caused by different manufacturers. We control for variation using weight, cargo capacity, and performance variables. We also perform a sensitivity test by removing the Cybertruck, since it represents an extreme case. This allows us to confirm that our results are not driven by a single outlier and strengthens the reliability of our model.
Our dependent variable is MPGE, which measures efficiency. Our independent variables include vehicle weight, cargo capacity, and performance trim. These variables capture the key trade-offs between efficiency, utility, and performance. The model estimates how each variable contributes to efficiency loss. The Cybertruck is included as a benchmark because it represents an extreme in utility-focused design. Its large weight and cargo capacity make it ideal for testing how efficiency behaves at the upper limits of vehicle size and functionality. This slide shows that our dataset has strong variation. MPGE ranges widely, indicating meaningful differences in efficiency. Weight and cargo also vary significantly. This variability is important because it allows the regression model to estimate relationships more accurately. The visual also shows that heavier vehicles tend to cluster at lower MPGE values. This slide summarizes the distribution of the data. The key takeaway is that the dataset has enough spread across all variables to support meaningful statistical analysis. This slide shows average efficiency across Tesla models. We begin to see that larger vehicles tend to have lower MPGE, which sets up the analysis that follows. This slide shows that efficiency varies even within the same model. This highlights the importance of analyzing individual configurations rather than relying only on averages. These distributions confirm that both MPGE and weight are widely spread. This strengthens the reliability of the regression model. Slide 15 shows that performance trims reduce MPGE, but the effect is relatively small. This suggests that physical design plays a larger role than performance branding. Slide 16, weight versus MPGE. This is the strongest relationship in the dataset. As vehicle weight increases, MPGE consistently decreases. This confirms that weight is the dominant driver of efficiency loss. Slide 17, cargo versus MPGE. Cargo capacity also shows a negative relationship with MPGE. This indicates that utility comes with an efficiency cost, separate from weight. Slide 17, cargo versus MPGE. Cargo capacity also shows a negative relationship with MPGE. This indicates that utility comes with an efficiency cost, separate from weight. Slide 19, regression. The regression model quantifies these relationships. Weight has the largest negative impact on efficiency. Cargo capacity also contributes significantly. Performance trim has a smaller effect. This confirms that physical design is the primary driver of efficiency. Slide 20, quadratic. The quadratic model shows that efficiency loss increases at higher weight levels. This suggests a non-linear relationship where heavier vehicles experience larger efficiency penalties. Slide 21, model strength. The model explains approximately 91% of the variation in MPGE. This indicates strong explanatory power and a well-fitting model. Slide 22, diagnostics. This slide confirms that the model assumptions are satisfied. Residuals do not show major patterns, and the model remains stable. Although some variables are correlated, they still provide meaningful information. Slide 23, Model Fit. This slide shows predicted versus actual values. Most observations fall close to the line, indicating strong predictive accuracy. Slide 24, Sensitivity. Removing the Cybertruck does not significantly change the results. This confirms that the model is robust and not driven by a single extreme observation. Slide 25, Economics. This slide connects efficiency to cost. With reduced impact from tax credits, efficiency becomes more important in determining total cost of ownership. Slide 26, Decision Implications. This slide translates analysis into decision-making. Buyers must balance efficiency and utility. Lighter vehicles offer better efficiency, while larger vehicles provide more utility at a cost. This reflects a trade-off that depends on the buyer's priorities. Slide 27, Limitations. This slide defines the scope of the analysis. The sample is small, limited to Tesla, and does not include all possible variables. These limitations define the context of the results, but do not invalidate them. To conclude, weight is the primary driver of EV efficiency. Cargo capacity adds additional cost. Cybertruck highlights these trade-offs clearly. Efficiency is driven by physical constraints, making EV choice a trade-off decision. Slide 29, Future Research, outlines possible improvements. Future work could include more vehicles, additional variables, and more advanced models to improve accuracy and generalizability. Slide 30, References. This slide lists all sources used in the analysis. Thank you for your time, and we welcome any questions.